This UCSD TV program is presented by University of California Television. Like what you learn? Help others discover UCTV podcasts by leaving a comment or rating for us in iTunes.
Welcome to this Charles David Keeling lecture. This is my first, and so I'm really looking forward to sharing it with you. The past few days have been ones where climate has been very much in the news. About a week ago, the U.S. released its third national climate assessment. And the very strong message from that climate assessment was that climate change is no longer something that's just in the future. Its impacts are upon us already. And that was a very sobering message, and one that I can assure you the scientific community was concerned to hear. We've also, in the last few days, received media attention from around the world concerning the Keeling curve. That was Charles David Keeling's research program to measure CO2 continuously, and that has been carried on since he stopped running the program by his son, Ralph Keeling, who you're going to hear introduce David Victor. And Ralph Keeling's research group reported May 1st that April 2014 was the first month in human history in which the concentration of greenhouse gases, carbon dioxide, not greenhouse gases in general, in the atmosphere stayed above 400 parts per million for the entire month. So that also was quite a sobering reflection for the entire community. The choice of David Victor as tonight's Keeling lecturer is also especially timely because discussion of climate change has moved beyond just the detection of it, the attribution of it, but spurred by the knowledge that it is already happening, has moved into the issue of adaptation and how we're all going to deal with this in the present day. And that really brings climate change to society. And so it's very important for us to start broadening our discussions beyond the scientific community into the social science community. We're going to require help from economists to help us understand the implications of decisions that we have to make, the practical decisions about how to adapt to climate change. Where do we draw the line between protecting assets and maybe having to abandon some of our assets? How do we adapt what we're going to face to our personal values? Messages that people should make prudent decisions after important floods or wildfires about the implications of that for where they live. Municipalities discussing how to share water rights for dwindling water resources. These are the kinds of questions that lead us into the real world and into the politics of climate change and the social science. And those are questions that David Victor has been considering for many years. He is an author of the most recent Intergovernmental Panel on Climate Change. And in fact, he was telling me just a few minutes ago that the whole first couple of weeks of class, and he's teaching 4 classes this term, he was commuting to Berlin, where the Conference of the Parties was doing the summary for policymakers. So he would go for a couple days, come back and teach for a couple days, and then go back to Berlin. That's the kind of dedication that all of the members of the IPCC assessment have shown. So he's been upfront row observer of the political gridlock that has waxed and waned over the past decade, and he's going to share some thoughts with us about that. And now to tell you, I've told you a little bit about what his field is, but to tell you a little bit more about David himself, I'd like to welcome Ralph Keeling, son of Charles David Keeling, and the steward of the CO2 measurements that were started some 50, how many years ago? 56 years ago. Ralph.
So thank you, Margaret. And the Keeling Lecture, we have each year we invite a prominent member of the global climate change community to give a talk that somehow reflects in an appropriate way the legacy of my father's work. His work was, of course, confined to the science of global warming and particularly of CO2, but the legacy includes topics that relate to impacts and what the society should do about it. And this year, I'm pleased that we can bring someone in who reflects a more human dimension of the problem, having to do with the politics and the negotiation, having to do with trying to make progress towards treaties to reduce greenhouse gases. So it gives me great pleasure to welcome David Victor. He's a professor of international relations at the School of International Relations and Pacific Studies here at UCSD, sometimes known as IRPS. He's also director of a laboratory of international law and regulation at the program. And a little bit of background, he received a BA at Harvard, and I've learned that we crossed paths a bit at Harvard, although I think we just narrowly missed getting to know each other because we were TA in the same course in different years. He moved on to get a PhD in political science from MIT. Before coming to UCSD, he was a professor at Stanford Law School, where he also served as director of the program on energy and sustainable development. One measure of his impact is the large role he plays in an advisory capacity. And I could go on at length here, but just a couple prominent ones. He's currently a member of the Advisory Council of the Electric Power Research Institute and has been on the board of directors there since 2013. Interesting one here. He's the chairman of the Community Engagement Panel established earlier this year to deal with communication and outreach having to do with the decommissioning of San Onofre Power Plant. So obviously a delicate and interesting process going on there. Earlier in his career, he also directed the Science and Technology program at the Council of Foreign Relations in New York. And he's the author of a very highly acclaimed book called Global Warming Gridlock, which takes on the question of why the world hasn't gotten further with negotiations on climate change and suggests some solutions to that. And I expect we'll be hearing a little more about that theme in his talk tonight. The book was recognized by The Economist magazine, as one of the best books in 2011. So for those of you who still read books, and I realize it's a dwindling list, it might be something to have a look at. Anyway, it gives me great pleasure to welcome David Victor.
Well, thank you very much for that introduction, Ralph and Margaret and Nigella. And I'm pleased to see Louise Keeling here and all of you tonight. It's really a pleasure to be here and to speak about the situation with climate change. My lecture tonight I've titled Getting Serious About Climate Change. The theme that I'm going to develop is that so far, at least from a policy point of view, we have not gotten serious at all. We've basically done nothing for the last 20 plus years. So I'd like to talk a little bit tonight about what we might do that's different. I'm going to speak for about 40 minutes, about half of it on where the natural science stands, including the work on climate change impacts, and then half of it on emissions and policy and so on. And it's an interesting time to talk about climate change because, as Margaret said, we've had a whole series of reports that have come out in the last year, and I've been very heavily involved to the point of commuting to Berlin, which is something I can strongly recommend against. I've been very heavily involved in the process of the Intergovernmental Panel on Climate Change, which has just finished its 5th massive assessment. Every 7 or 8 years now, we do these assessments. It requires about 7 or 8 years between the assessments because you have to forget what the experience is like before you agree to take on another one of these. And the first of the 3 reports that we put out was published last September. It's about the underlying physical science. The second came out in March. It's about impacts and adaptation. And the third, which I've been centrally involved with, came out in April, so a month or so ago. And it's about what we call mitigation, but it's really about emissions trends and controlling those emissions. I was reminded, as Ralph and I reminisced about old times a while ago, about this overlap that we had at Harvard teaching the atmosphere. The class was called The Atmosphere, Science A30. And I don't know if I deserve kudos for writing up all of those notes. I do remember being tremendously naive as a young student and thinking, how hard could this book writing thing be? We had all these notes. They were on view graphs, and some of them probably were on papyrus for all I know. And so I just wrote them up into a book, and it was, I think, one of the worst books ever written on this planet. In 3 years, we are going to celebrate the publication, the 60th anniversary of the publication of a very important paper in the history of climate science by Roger Revelle and a co-author, which was the first paper to put together fully the buffering chemistry of carbon dioxide in the oceans. And until that paper came out, a lot of people could plausibly assume that carbon dioxide that went in the atmosphere, and there were not very large industrial emissions, but some significant emissions at the time, carbon dioxide that went in the atmosphere would all end up in the oceans and kind of stay there, or at least we wouldn't have to worry about it too much. And Roger and his colleague said, no, that's actually probably not correct, and here's the reason chemically, because the carbon dioxide would mix into the oceans and then generate some acid in the oceans, and the bulk of it would net stay up in the atmosphere. But that was a hypothesis, and in order to know whether the hypothesis was sound, you needed to go off and reliably measure atmospheric concentrations of carbon dioxide. And that had been done a little bit here and there with ad hoc methods. People, when they flew across the North Atlantic a lot, they were taking measurements out of airplanes and other kind of cool things, but there was no reliable record, and of course, as everyone knows, Roger raised money from the Office of Naval Research and a variety of other places, hired Dave Keeling, and they went out initially to Hawaii and then other sites and started measuring carbon dioxide concentrations in the atmosphere. This slide here shows you where we stand, and as Margaret mentioned in her opening remarks, last year we were flirting with 400. This year we've had a whole month that has flirted with 400, and then eventually it'll be a whole year and so on. The pre-industrial concentrations, so that the time before the Industrial Revolution that was powered by fossil fuels and continues to be powered by fossil fuels, concentrations were on the order of 280 to 290, 300 parts per million, and now we're seeing concentrations reliably up in the 400 range and no sign of that slowing down. Almost everything that I'm going to say tonight concerns the climate change that follows from the buildup of carbon dioxide and other greenhouse gases. I will say that one of the byproducts of the analysis, really going back to Roger Revelle and a handful of other people, is also that the oceans would become more acidic, or the surface oceans would become more acidic, and that's in fact exactly what you measure. Here are measured pHs in the oceans. We've seen the oceans become more acidic by 30 or 40%. They're naturally variable to some degree. And that on its own is a significant concern, especially for ecosystems that depend heavily on making shells for a living, and there are very many important ecosystems in that regard. It's interesting to reflect that if you summarize the state of climate change science today in a small number of figures, which is in fact exactly what we did in the IPCC in our first report last September, where we had in our summary for policymakers 10 figures, this is one of them. So the contribution that Dave made and Roger Revelle and Scripps made to this topic has been just profound, and it remains tremendously durable. And it's a contribution that Ralph carries on and many others, and we're enormously grateful for them for their work. Because really the whole discussion about climate change begins with reliable measurements that the gases we're concerned and pollutants we're concerned about are building up in the atmosphere. People often ask, how do you know that this is not naturally variable? And this is a topic that the IPCC and a series of climate modelers who've done a large climate model intercomparison project I've worked on extensively in the last few years. This slide here just summarizes where that work stands. What it shows you is a compilation of different ways of measuring changes related to climate change. Some of these figures are changes in temperature. Some of these are changes in OHC, the ocean heat content, and some of these are changes in the sea ice extent in Antarctica, very much in the news in the last few days, and in the Arctic. And what you see here is an effort to tell the best models we have in the world about the buildup of greenhouse gases in the atmosphere, and then to compare that with the actual observation record. And so you see for every single one of these little vignettes, and these are summary vignettes for global averages over here, for land surface temperatures, which are the most responsive to changes in climate, ocean surface temperatures, so thermal inertia in the ocean, and then the ocean heat content, what you see is that if you just tell the models about natural variability that we know about, what you see are these blue patterns. And if you tell the models about natural variability plus the buildup of greenhouse gases in the atmosphere, what you see are the pink bands with the actual observation and record shown in the black line in the middle. Almost everywhere, we're not yet at the point where this is true everywhere, but almost everywhere, you simply cannot explain what you observe in the real world without telling the models that there's been a buildup of greenhouse gases. And that gives us confidence in the models. It also gives us the ability to say things like it is extremely likely that the majority of the observed climate change, warming in the atmosphere since 1950 is caused by humans. So this is an area of ongoing science, but I have to say statistically, the results are just profound. And one of the major contributions that the science team and the IPCC has made has been to be able to really nail down that we are seeing the signature of the human impact on the climate. It doesn't mean that we know everything, and in fact, in very important ways, the uncertainty around climate change science has actually gone up rather than down, and I'll talk a little bit more about that, because it's not that we've become more stupid over time, although maybe that's the case. Certainly my 4-year-old thinks that's the case, but it's that we're learning things that are in the realm of the unknown unknowns, if you like, and those become, I think, actually, on balance, scarier the more we learn about them. The kind of uncertainties, or the fat tails, as some people call them, are deeply worrisome in this area. I just want to point out that the phenomenon of global warming, which is the kind of general popular term, and it kind of sounds friendly, like warming and so on. So a lot of people in the climate community has not been so thrilled about that, nor in the scientific community, so we call it climate change, but nobody really knows what that means. So some people like to call it climate weirding, but that just sounds weird, and so we have not actually come up with a good term to convey what's going on here. But the phenomenon is caused not only by carbon dioxide, which is what Roger Revelle worked on and Dave Keeling measured so extensively, but a variety of other gases. And I just want to give you a summary of those other gases, and I'll talk a little bit more about this later. The picture up here is not so great, but what you see on the top is carbon dioxide, and the bars show the amount of change in the heat balance in the atmosphere, measured in watts per square meter since the pre-industrial period. So these are very, very small numbers. Think of a watt per square meter as one of those old tiny little Christmas tree bulbs, a little 1-watt bulb over a 1 square meter surface area. That's the amount of change in the heat balance in the atmosphere. And it's a tiny number compared to big numbers like the incoming solar radiation, which is more than 300 watts per square meter, the amount of radiation that the planet radiates back into space. Those are huge numbers. We have small changes caused by these trace gases in the atmosphere, and it's those small changes that then cause the change in overall radiative balance and climate warming. Since 1750, the amount of that perturbation caused by carbon dioxide is about 1.7 watts per square meter. The next most important gas is methane gas. Methane gas comes from growing rice, comes from cows. Cows vent methane from both directions, sheep, a variety of other ruminants and so on. And methane gas is now contributing about 1 watt per square meter, and then on down from there. Very much in the news from work here at Scripps are aerosols. Black aerosol, also known as soot, which is a very large net warming agent, and then other aerosols like sulfate precursors that come from burning high sulfur coal in power plants without pollution control equipment. Those actually cause a net cooling effect in the atmosphere. When you think about this problem as a geophysicist, you look at this and you say, yeah, there's different gases involved, but this is really a carbon dioxide problem. And what I'd like to suggest to you as my talk goes on is that when you think about this as a political scientist, which is what I am, that these other gases are actually really, really interesting because their political properties are very, very different. Carbon dioxide is an extremely difficult gas to control because it is intrinsic to the combustion of fossil fuels. And fossil fuel consumption is intrinsic, more or less, to modern economies and is very, very expensive to limit. Whereas the other gases, we actually know a lot about them and their impact on climate could be very, very large. So you cannot stop global warming over the long haul without solving the carbon dioxide problem. But politically, part of the difficulties we've seen in the last few decades is that we've been thinking about this in an almost obsessive way as a carbon dioxide problem and not paying enough attention to the other gases such as soot and methane and so on. Kind of what's at stake here. This next slide shows you, this is historical data. The shading is the variability in those different data sets from 1950 to essentially the present. And then these are model projections using the same models that I showed you before, model projections going out into the future. And this blue line down here is you tell the models we're going to stop the buildup of greenhouse gases in the atmosphere at 2.6 watts per square meter, which is roughly today's total, just slightly above today's total. So that's like an aggressive crash program to control emissions, and I'll show you in a little bit what that actually might mean. And then these lines up here are basically everybody just keeps doing what they were doing in the past, so-called business as usual, where you continue to grow the consumption of coal aggressively and other fossil fuels and maybe cut down some more trees and so on. And all of that results in a greater buildup of carbon dioxide and other greenhouse gas in the atmosphere. And then you end up with radiative forcing of 8.5 watts per square meter. These are models, these are projections done by climate scientists who love watts per square meter. I'm a political scientist and I like to worry about controlling emissions, and so I like carbon dioxide concentrations, and so I'm going to shift in a little bit to talking about that. But this gives you a sense of what the bookends are. This is if you have a worldwide crash program, you can stop global warming at what appears to be significantly below 2 degrees. If you don't do anything, then we're on track by 2100 to have warming on the order of 4 degrees. And so you've seen in the news people worrying about a 4-degree world and so on. And that's 2100, and then it continues on after that. These are worlds that are actually, I think, outside the realm of our capacity to understand what the potential impacts of that are. Let me talk a little bit about the impacts, and then I'm going to stop with my kind of summary of where the science stands so far. This next slide shows you the impact where I think we have perhaps the greatest confidence, which is the rise in sea level. Although the news over the last few days, not all of it unexpected, is a kind of confirmation that there are still a lot of very interesting in a kind of perverse way of the word interesting, but interesting surprises in this science. Again, the blue lines here are the RCPs 2.6, so this is the crash program. The red line up here is 8.5, so this is we sit back, drink Mai Tais, and don't do anything about the climate change problem. By the year 2100, you see potentially kind of 0.6, 0.7 meters of sea level rise up to, and this is the uncertainty, 5% to 95%, up to almost a meter. So this is where this 3-foot number comes from, is that sea level rise might be up to 3 feet. When people say that, they are thinking about the upper band of the uncertainty around the Mai Tai scenario. You're just sitting around doing nothing about the climate change problem. And whereas if you have a crash program and you're lucky, then sea level rise is barely noticeable. What's interesting on this chart, in my view, is it also gives you a little bit of a window into the areas where there's uncertainty. You can think of this uncertainty between the blue line and the red line as an uncertainty about how humans are going to respond, the socioeconomic system, how we're going to respond to the evidence of climate change and potentially control our emissions. And then you can think about the bands around each of these as the natural uncertainty, the geophysical uncertainty about how the climate system itself actually responds. And what's interesting to me, and there's been several papers that have tried to look at this in more detail, is that the uncertainty around the socioeconomic systems is about as large as the uncertainty in the natural systems. And I think when you do the analysis correctly, it's actually even larger. So we've got we're throwing lots of dice, and we just simply do not know how they're gonna turn up. This is an area where the uncertainty between this current, most recent IPCC report and the previous IPCC report has actually gone up. And it's because the previous report basically reported relatively little information about melting glaciers and only focused on the source of sea level rise, really basically only focused on the source of sea level rise that was easiest to quantify, which is thermal expansion of the oceans. When water gets warmer, it expands, and so you can quantify that, with relative precision. And now we know much more, thanks in part to work here at Scripps, and I've learned a lot about this from Walter Munk in particular. We know a lot more about what we don't know about how grounded or landed ice sheets move and respond to melting, and in particular in Greenland and in the West Antarctica. Some of the other impacts that are important to keep an eye on is precipitation. In general, a warmer world is a wetter world because it has a more active climate system, but it's wetter in the places that more or less are wet already. So if you look down here, for example, this is what the late 21st century might look like under the Mai Tai scenario, basically people not doing anything to control emissions. You see this big increase in rainfall around the intertropical convergence zone. This is a very stormy area. Those of you who follow the Air France flight from Brazil to France that flew through some of the superstorms in the intertropical convergence zone know that this is a very stormy and dangerous area. And then deserts, like in North Africa, the Mediterranean area more generally. California's a little harder to pin down, although some finer resolution work done in part by folks here at Scripps have shown that the desert areas are likely to get, if anything, anything drier. And so you can then imagine what these kinds of impacts have on agriculture and other parts of the economy that are exposed to changes in climate. One last word about impacts, then I'm going to talk about what we're doing or not doing. In my view, the impacts that are most important to watch are the ones on natural ecosystems. And that's because there's a huge gulf in the scientific research between people who study impacts of climate change on human ecosystems or human systems and impacts of climate change on natural systems. And that's because humans, we don't always do it, but we can look ahead and we can say something's coming and we can respond, we can adapt. And the way that humans adapt to climate changes has a massive impact on the overall net impact of the changing climate on the economy. Whereas nature doesn't do that. Nature responds through extinction and evolution. And so the impacts of climate change on natural unmanaged ecosystems could be truly profound. And this slide gives you a sense, for example, for different natural ecosystems, trees, herbaceous plants, rodents, insects, freshwater mollusks. Apparently a lot of work's been done on the mollusk. That's news to me. And the speed at which they can move. How many kilometers can you march around per decade? Which is a kind of first cut for getting a sense of how responsive the ecosystem might be to a change in climate. And so if you have even small amounts of climate change on flat areas, that can result in a pretty significant displacement over land. And this gives you a sense of these different scenarios. RCP 8.5 or in flat areas is going to result in displacement of natural ecosystems nearly 100 kilometers per decade. And so I think that it's possible that the mollusk will catch up with that. Mollusks are very fleet-footed, apparently. Trees, of course, have a harder time marching because the natural cycle of most trees is long, and the extent to which they can spread seeds and other methods of propagation are limited. This is raising, or should be raising, profound questions for the ecological community and people who care about nature in a kind of deep sense of nature, because it does raise the question of where and how we are going to intervene directly in nature to try and control and help nature adapt to climate change. And it may well be that in some pristine natural ecosystems, because of the impacts of climate change, we're actually going to find ourselves kind of becoming farmers or zookeepers, if you like, and actively helping natural systems to adjust and adapt, rethinking the way we do protected areas. Right now, when we have very special ecosystems, we put a fence around them. Maybe fences are in fact exactly the wrong thing to be done to do, and you instead ought to have corridors, especially kind of north-south corridors that allow species to move along different climatic zones. Okay, that's a kind of summary of where we stand in the science. When I look at that in total, it's pretty scary. And so what are we actually doing to respond to that? And the short answer is we're doing pretty much nothing globally. This is a slide from the most recent IPCC report, the one on mitigation of emissions, which I worked heavily on. It shows since 1970 up to the present Emissions of all the different greenhouse gases added up using different units. So carbon dioxide is down here. Carbon dioxide from land use change, which is right in there. This is actually one of the few bright spots, is that net deforestation in the world is now roughly flat. And there's a lot of serious people now talking about global greening. We've had for decades now a rebound of forests in high latitude areas like the United States, China, Russia, and so on. We're now starting to see the beginnings of a rebound in some parts of the tropics, certainly not all the tropics yet. Nitrous oxide, methane, and so on. 2010 was the highest emissions we saw on record. The last decade alone, we've seen emissions grow more rapidly than any decade since 1970. At 3 a.m. on a Saturday morning in Berlin for one of these trips, I negotiated with a Chinese delegate to remove all of these markers here that tell us how much the different decades grew, because the Chinese were upset that since they're mostly responsible for the growth of emissions in the last decade, they didn't want it to be quite so readily comparable with other decades. And so you'll see in the final version of this, you'll see that they're actually all lumped together. But no matter how you slice it, emissions are rising rapidly. You say, well, how is that possible? Because we have international treaties in this area. We've had, since 1992, a Framework Convention on Climate Change. We've had the Kyoto Protocol, which was finished in 1997. We're negotiating new treaties right now. There'll be a big summit at the UN in September of this year, and a big effort by meeting in Paris next December to have a new treaty to succeed the Kyoto Protocol, which finally expired in the year 2012. Given all those treaties, how is it possible that we could be in a situation where emissions are rising more rapidly during the decade when you would expect all these treaties to be having an effect? And the reason is that we have become incredibly skilled at designing treaties precisely so they have no impact. Here's an example from Kyoto. The Kyoto Treaty lists all the countries that agree to control their emissions on the back of the treaty in a list, Annex B, and it's stapled to the back. And that list of countries is basically the members of the OECD, which is the Rich Countries Club at the time, plus the Russians, who were keen to be in the Rich Countries Club even though they really weren't in the Rich Countries Club, and Ukraine, which was tethered to Russia, as they've now learned, maybe not so greatly. And if all those countries that were listed in Annex B had actually controlled their emissions, they would have had leverage on about 60% of the world's emissions at the time. So 60% of the countries that represented 60% of the world's emissions agreed in Kyoto to start doing something about controlling their emissions. Now that leaves out still 40%, but 60% is a pretty good down payment. But then if you look at the countries that actually stayed inside Kyoto, so you remove the United States, you remove Canada, because Canada joined the Kyoto Protocol on the assumption that the United States would join the Kyoto Protocol, which is its largest trading partner, and then looked in the rear vision mirror and discovered we didn't join. So then the Canadians actually withdrew. And then you get down to 23%. And then if you look at the countries that agreed to stay inside the Kyoto Protocol, once the Kyoto Protocol a couple years ago was updated and extended out to the year 2020, you have only 13% of world emissions. Japan left at that point, the United States stayed out, Canada stayed out, and the countries, which is mainly Europe, that stayed in, their emissions are largely flat or declining, and all the rest of the world's emissions, China and India and so on, continue growing. So the Kyoto Protocol Treaty today only tells us something about 13% of world's emissions, and the rest of it is completely omitted from that, and that's because countries can pick and choose which international obligations they want to sign up to. And then if you look at the countries that actually were members of Kyoto, so here is a chart showing the emissions between 1990 and 2010. 2010 is the center point of the year of the regulatory period of the Kyoto Protocol. And then I list the countries along horizontal axis here. This is Ukraine, Russia, the original 12 members of the European Union, the next 15 members of the European Union, Japan, Australia. These are all countries that joined the Kyoto Protocol and stayed inside. You see that they have some very impressive emissions reductions. And that group as a whole complied with their general obligation to cut emissions about 5%. Why is that? It's dominated by Russia and Ukraine. They didn't control emissions because they're worried about climate change. They controlled emissions because their economies collapsed. And when your economy collapses to first approximation, your emissions go down. In fact, I would say most of the Russian scientists at the time were telling the leaders, you know, this is a cold country and maybe we'd be better off with a little bit of climate warming. Europe has done a little bit. We, a couple years ago in our lab, did a counterfactual calculation where we looked at how much did Europe control its emissions because of the presence of the Kyoto Protocol. We came up with a number of about 200 million tons. That sounds like a big number. That's roughly 3 weeks of growth in the world's emissions. So all of this diplomatic effort has had an impact of slowing growth in world emissions by roughly 3 weeks. What do we know about what causes emissions? This is a slide from our most recent IPCC report that looks at different decades, 1970s, 80s, 90s, the most recent decade, and decomposes the growth in emissions into different factors. Carbon intensity, that's the amount of carbon per unit energy. So coal, for example, is much more carbon intensive than oil and natural gas, and nuclear power or renewables, for the most part, don't have any emissions. Energy intensity, this is the efficiency with which the economy basically turns energy into economic output. Population, shown in the blue here, and in the orange, GDP per capita, growth in the economy. And what you see is that consistently, the economies, these green segments of these bars, are always negative. Economies autonomously become more efficient because they change in structure, because there are incentives for efficiency and so on. And those are not enough to offset the overall growth in emissions, but they have a pretty big impact. Until the most recent decade, economies also autonomously moved from high carbon fuels like coal to lower carbon fuels like natural gas. And one of the most striking results of the science in the last few years has been to demonstrate now that the world's energy system is in fact recarbonizing. Net use of coal is going up, including some perverse things like we are exporting coal from the United States to Europe to burn in German power plants and a variety of other, and British power plants. But the big rise in coal consumption has come from China and from India. Population is something people worry a lot about. Population growth has been roughly flat. My own view is that population is not a major problem. The central largest driver for emissions is growth in the economy. So absent policy, economic growth, which is what almost everybody wants, economic growth begets emissions. And that is the kind of central challenge here. When you look over the last 2 decades, between 3 decades, between 1990 to 2010, and you ask yourself, how about per capita emissions? So this is a plot, this is a kind of unusual plot. This shows on the vertical axis per capita emissions, tons of carbon dioxide per year, and then on the horizontal axis, the cumulative population. So here you have the highest emitters, Central African Republic, Qatar, Kuwait, and so on, very small populations, very large emissions. And here's the United States, for example. And as we accumulate up the populations, here's China and here's India. And what we show on this chart here is the difference between 1990 and 2010. And the green basically is a net reduction in per capita emissions from mainly high industrialized countries because their economies are becoming more mature, because some of them, like the Europeans, are actually adopting policies in this area. And then the rise in per capita emissions from the emerging economies, India here, and especially China. Net world per capita emissions today are essentially identical to what they were in 1990. What's happened is a huge shift in the world economy from the basically flattening of the industrialized countries to the tremendous growth in the emerging economies. And along with that growth has come a transfer of emissions, in effect, from developing countries to industrialized countries. And that's because when you make a ton of steel in China, for example, and you put the steel on a boat and you send it to the United States, the Chinese, in some sense, get charged for those emissions because all of our statistics until recently have been organized on territorial grounds. But the world economy doesn't function that way anymore. In effect, what the Chinese are doing is sending embodied emissions from China to the United States. This slide gives you a sense of what that process looks like between the high-income countries, the upper middle-income countries, China, India, Malaysia, other rapidly growing countries, lower middle-income countries, and the least developed countries down here. And let's just focus on the emerging economies and the rich industrialized economies. The bars here show us the net import in the case of the high industrialized countries and the net export in the case of the upper middle income countries. The Chinese alone today are sending at least 600 million tons of emissions per year equivalent embodied in the products, wallboard, spans of the Bay Bridge, because huge sections of the Bay Bridge have been actually imported, already assembled, into the industrialized countries. And so when you look at industrialized countries that have done a lot on paper to control their emissions, in fact, a huge part of what they've done is in fact outsource those emissions. We have to find a solution to this problem. Part of the solution is going to involve border tariffs and trade policies that get the incentives right. This is something that trade economists are extremely worried about because it might involve tinkering with the trading system that has been so successful. But until we get those incentives right, in effect what we've done is we've created an incentive for countries that do a lot to regulate their emissions to allow emission-intensive industries to migrate outside their borders and go to other parts of the world. You see this today, for example, in the mass migration of the steel industry out of Europe and into other parts of the world. In some cases, actually, migration with the plants. They've taken entire steel mills, put them on barges, and sent them to India, for example. So last slide, I want to show you about where we stand in terms of emissions, and then I want to pivot and talk a little bit about ways we can do better, and then I'm going to stop. Just to want to give you a sense of the size of the challenge involved here. So this slide here shows you from 1850 up to the present. This black line are world emissions of all the different greenhouse gases. Here we see in the last century this kind of significant rise in emissions. And then these different scenarios show us the level of emissions that might exist in the future using a variety of different computer models. These up here are the business as usual kinds of models. These are the Mai Tai scenarios. You just sit around and do nothing. That's what the economy will give you. These scenarios here are scenarios where you assume we go as aggressively into energy efficiency as possible. Those scenarios, interestingly enough, don't even stop the growth in emissions. These scenarios are the ones that actually let you stop warming at something like 2 degrees. The baby blue ones are a high likelihood of stopping warming at 2 degrees, and these yellow ones are a 50-50 chance of stopping warming at 2 degrees. There's a key insight here, which is here are emissions today. There's 2050, which in the energy business is tomorrow because so much of our energy infrastructure is long-lived. By 2050, world emissions have to be less than half what they are today. That gives you a sense of the scale of the challenge. And you can look at this in different time periods. This is the slide that I showed you earlier about the recent history, showing very clearly the trends are all in the wrong direction. This is what the next 20 or 30 years looks like. So these are the same baby blue and yellow scenarios. These are the pledges that governments signed up to after the Copenhagen meeting and another meeting the year later in Cancun. These are what governments said they would be willing to go off and do on their own. So the Cancun pledges, things that governments say they're prepared to do already, are only if we're lucky consistent with some scenarios that give us a 50-50 chance for stopping warming at 2 degrees. And in the long term, out in the future, the picture is just bleak. Big reductions in emissions are going to be required. Let me let you in on a secret in these models, which is these models are optimization models run by economists. So the model looks forward and it says, and it identifies the least cost way of controlling emissions. The models don't know very much about how humans get in the way of that process, usually making things more expensive. For example, we simply say some technologies will not be allowed, say nuclear power, for example. If you remove nuclear power from the equation, costs go up. If you remove renewables from the equation, costs go up. These models love a technology called carbon capture and storage, CCS. CCS is a really interesting technology. What you do is you take a power plant, you capture the gas at the end of the power plant, and instead of letting it go up in the atmosphere where it builds up and causes global warming, you capture it and you inject it underground, safe so it doesn't cause a climate change. And CCS is really interesting, except for the fact that there are basically no plants actually being built in the world, so we don't know what CCS really looks like at scale. From the plants that have been built, the cost overruns have been just astronomical. This is a very, very expensive technology. The modeling community decided that even though CCS, which is its favorite technology, even though CCS is kind of a fantasy, we now have a new favorite one, which is called bioenergy CCS, BECCS, B-E-C-C-S. And bioenergy CCS, you go out in the world, you grow plants, somehow you harvest the plants without causing emissions. That's some kind of miracle occurs there. You get the plants into the power plant, you burn them, or you co-fire them with coal. You then capture the carbon dioxide and inject it underground. So those plants have negative emissions. Why do the models love this? because it allows the model to assume that we as humans aren't going to do anything about controlling our emissions for the next few decades, and then there's going to be some crash program in the future where emissions are going to come down really quickly. And that's what you see are these scenarios where these huge reductions in emissions become necessary. This is why the modeling community says it is still technically feasible to stop warming at 2 degrees. In my view, a world where you are not smoking and inhaling, 2 degrees is not feasible. There is no plausible scenario by which stopping warming at 2 degrees, which is the most widely discussed goal for climate change, is going to be feasible. And we need to start thinking about alternatives and so on. I want to just talk for a moment before I close about the question of whether we can do better. I don't want to be a naysayer or kind of a, Bill Safire I think called a nattering nabob of negativism on the issue of climate change policy, but it's hard, having studied this for a long time, looking over the last 20 plus years of diplomacy, not to come away with a conclusion that we basically have been messing around at the margins. And we've done a little bit here and there, but it's mostly symbolic. And we're nowhere near getting serious about cutting emissions 50, 80%, and so on that might be necessary to stop warming at 2 degrees. We've done that in part because this is a hard problem. This is a really, really hard problem. It has all the attributes that we as humans don't deal with very well. For example, it's caused by the long, slow buildup, mostly not visible, of a pollutant. It requires doing costly things today for benefits that are uncertain and distributed into the future. We tend not to be very good at those problems with high time inconsistency and so on. And so I think it's not surprising that we haven't done well by this problem, and no technological miracle has come along to make it suddenly cheap or unnoticeable to switch to zero carbon fuels. Technological miracles largely explain the success with the most successful international environmental problem to date, which is the ozone layer. Technological miracles came along. They turned out to be not very expensive. International law helped a little bit here and there, but there's nothing like having good technology at low cost available. So how can we do better? I want to just talk in my final few minutes about 3 ideas. One is we should rethink our relationship to the UN. The UN has a lot of very important benefits. And one of those benefits is that by having an institution where essentially every country has a voice, you have legitimacy. But the problem with that is you also have gridlock, because any country that's unhappy with the outcome can simply say, I'm not going to join that agreement, or can block the agreement altogether. Or at 3 a.m. between the Chinese and the Saudi Arabian delegation, we could not insert. We removed 1/4 of all the figures in the summary for policymakers for the last IPCC report because of objections by 3 or 4 countries, led by Saudi Arabia and Malaysia to some degree. The Chinese certainly were not happy with this. And so it's kind of crazy that we have a scientific process, let alone a diplomatic process, that is victim, basically, to the interests of the lowest common denominator or the slowest boat. This is not unique to the climate change problem. This happens all the time. And one way to solve the problem is to start working in smaller groups and start gaining experience with cooperation in smaller groups. Clubs, some people call them. We used to call them coalitions of the willing, but then that term got used for something else. Didn't end so well. So that's out. And so if you look, for example, at a rank plot, so this is the biggest country in the world, which right now is China, a little more than 20% of the world's emissions of carbon dioxide, then the next biggest, the United States, and so on. If you look at a rank order plot, and the fraction of the world total that's covered by these countries, you see that for about a dozen countries, you get 75% of the world's emissions of carbon dioxide. And it's a comparable number if you look at all the other greenhouse gases here and there. So you can do a tremendous amount with small groups of countries. And in fact, we're starting to see some evidence of that. US-China dialogue on clean energy and a variety of other small group settings in this area. You know what, for me, what's interesting is that a huge part of what's needed in the climate problem is a big push on technology, basic spending on R&D, demonstration projects, and so on. And if you look at the concentration, the rank order plot for who actually is relevant in technology, which you can measure by R&D spending or measure by patents in energy-related fields, it's even more concentrated. So 4, 5, 6 countries in the world basically control almost all of the innovations landscape around energy. And so policy in those countries, along with cooperative firms, can make a big difference. The second of the 3 things I want to suggest is that we should go back to this chart that I showed a little while ago and think about this the way a politician would think about this. So carbon dioxide is the big kid on the block. We need to do something about carbon dioxide over the long haul, but it's politically hard because it's a long-lived gas. It builds up in the atmosphere. It's very expensive to regulate right now with known technologies. But methane is big. Soot is big. This number probably underestimates the size of soot. Soot has lots of other impacts as well. And so maybe we should work on some of these other gases. When you start doing that, the politics change completely. And they change for two reasons. First of all, these other gases are much more short-lived, which means that if you make a big program to control their emissions, then you see the benefits, in the case of soot, within the lifetime or tenure of politicians. And so the political calculation is totally different. And the other thing that's very interesting about these other pollutants is that they cause lots of local harm. Soot in particular is a huge killer. And so that means that countries that might not care very much about global climate change problems might nonetheless care about local pollution problems. And this is in the news practically every day now as the Chinese and the Indians try and struggle with soot and other kinds of pollution in their major cities. One of the calculations we did for the last IPCC report is we looked at, for black carbon, so soot, and sulfur dioxide, which is actually a cooling agent, we looked at what happens to emissions between a no climate policy and a stringent climate policy. And so if you aggressively adopt a climate policy, you get a big reduction on the order of 50% in soot. Or if you do the opposite, and you have an aggressive soot control program, as the Chinese do right now, you tend to adopt technologies that are more efficient, that move away from high carbon fuels like coal and in the direction of natural gas. We call this in the business co-benefits. You can walk and chew gum at the same time. But politically, it's really important because it means it's easier to hold countries that might be reluctant or flaky to do something about the global problem. You can hold them into your coalition. That is important for almost every country on the planet, including this one. And I think it's important in this country because the voters sometimes care about climate change and other environmental problems, and sometimes they don't. And public attitudes in this area are extremely fickle. And so if you sell this just as a climate problem, the voters are going to come, they're going to go, and it's going to be extremely difficult to get legislation, perhaps especially in the current environment in Congress. And you see this, for example, if you look at the Gallup polls. Gallup does a regular polling around environmental attitudes. They also do some stuff on climate change, which I'm happy to show in the Q&A period. This is, you ask people, should the nation put a priority on the environment, which is shown in green, or economic growth, which is shown as yellow, and which should have the higher priority? And it's extremely volatile. So you see, for example, after the Macondo oil spill, over a very brief period of time, people who thought that environmental issues should have a priority over economic issues went from 38% to 53%, and then it dropped back down within a single electoral cycle. And climate's the same way. When you do polling, careful polling on climate, it comes, it goes, especially it goes when people are worried about other things like economic growth and jobs. Last thing I'll say is we need to take advantage of accidents, of fortuitous things that happen that lower emissions, and we can use policy to then lock those into place. And one of those is going on right now in the United States with the price of natural gas. Because of fracking, which everybody's read about and I'm sure has lots of opinions about. It's actually horizontal drilling and fracking, but somehow fracking sounds scarier than horizontal drilling, so people's always talking about fracking. Because of fracking, the supply of natural gas in the United States has exploded, and the price, shown here in the white band, the price has now decoupled from the rest of the world's natural gas markets. The United States, only a few years ago, almost all the experts thought the price of natural gas in the United States was going to $6, $8, $10 a million BTU and up from there, and basically was coming out of the oil markets. Today, the price of natural gas is kind of in the $4-ish range, and serious people think it'll be $4 forever, or maybe $5. But this is a totally different world than the world we thought we were living in the past. Cheap natural gas appears to have been a tremendous boon for climate change, for concerns about climate change. And that's because gas is competing coal. Regulation by the EPA is helping as well, because coal plants are under a coal plant emits like the entire periodic table of the elements. And so the EPA, you can imagine, is very unhappy about that. So that fact, plus cooling water issues and so on, have put a tremendous amount of pressure on the coal industry. Regulation of coal, and especially cheap natural gas, are driving coal out of the marketplace. And total US emissions of carbon dioxide from the electric power sector, which is the sector where this competition is most intense, total emissions now are down by 300, maybe 400 million tons of CO2 per year. So maybe twice the entire European effort under the Kyoto Treaty, just because of the fortuitous accidents of cheap natural gas. Fracking is not without its own problems, including leakage of methane, which is a very strong greenhouse gas, and so it's very important to regulate that. But what I think what's interesting that we're seeing right now is EPA and other regulatory bodies are working hard to now lock into place a U.S. electric power sector that relies much more heavily on natural gas than coal, than was the case in the past, and that overall helps us keep our emissions down. It's not an 80% reduction in emissions, which is what we need ultimately, but it's a substantial down payment. And I think when you look at these three ideas, working in small groups as opposed to just in the UN, working in lots of different small groups, identifying co-benefits, so worrying about other parts of energy problems that are linked to climate, locking things into place when they happen, this helps explain why the actual policy landscape around climate change today is highly fragmented. It's not a single global UN treaty that sets targets and timetables and goals for all countries and then everybody follows that, which is more or less the strategy we followed in the case of the ozone layer. But it's a whole mess, a whole dog's breakfast of different regulatory efforts that are competing with each other to some degree. And a couple years ago, a political scientist, Robert Cohen, and I made a landscape of mapping of all of the different institutions, international institutions that are trying to affect climate in various ways. And this is what we found as a result of our mapping. And if you look in here, you see the formal UN legal regimes are only part of the story. And you have lots of small groups, clubs like the G8, now the G20, Asia-Pacific Partnership, a variety of others, a whole bunch of bilateral initiatives, and on and on and on. This vision of the world makes international lawyers extremely unhappy because they like clean, hierarchical legal systems. But it's much more realistic, and I think done properly, it actually could be more effective than what we've been doing in the past because it creates laboratories, places where countries can experiment and see what works, as opposed to relying just on the UN-oriented process, which so far has produced a very large number of meetings, a growing number of treaties and other legal documents, and no measurable impact on actual world emissions. And so I'd like to close by just saying that the ideas that I've offered here for how to make it better, I think are rooted in reality. I think the reality is they're not going to work quickly, not that what we've done for the last 20 years has worked at all. And they mean we have to contemplate a world where it is simply infeasible to stop warming at 2 degrees, where we're looking at a lot of adaptation. And we have to be able to talk about adaptation in a serious way and get ready for changes in climate and sea level. That's very important in San Diego, while also mitigating emissions. I think we can make some serious progress on mitigating emissions by starting on the emissions problems that are a little more tractable, that line up better with national interests, like the soot problem, not because they stop warming, but because they demonstrate credibility. And I think what's lacking in this area, at least in the policy world, is credibility. That firms now see that governments have been working on this problem for 20 plus years and haven't done anything. And firms no longer believe that serious rules are coming. Whereas 5 or 6 years ago, almost all serious firms believed that. And so they invested heavily in new technologies. And now, I don't see evidence of that, at least in the big emitter firms, hardly anywhere. And one piece of evidence of that is ExxonMobil a few weeks ago issued finally a report where it made an assessment of whether its enormously valuable carbon stocks, which is what oil in the ground is, were going to be degraded in value if governments started to control their emissions. And it said, yes, if governments started to control their emissions, these stocks would be degraded in value, but we think the probability of governments doing anything serious in this area is so close to zero that it has no material impact on our operations. And that's not a statement about Exxon. That's a statement about how the people who are ultimately going to fix the problem, how they see the credibility of what governments are doing. And so we've got to find a way to boost our credibility. And with that, let me stop and say thank you very much.